There you go. Start signing it. Pass that around. We were doing inductance last time. So let's start with the inductance of a solenoid, of a coil. We're going to take a coil of wire that has N turns, N loops, over a distance L, with an area of each loop, cross-sectional area, pi r squared. Okay, so that's, when we talk about the area, that's what we're talking about, the cross-sectional area of the physical coil of wires. Now we defined inductance as the EMF, the induced EMF is equal to the negative of the inductance times delta I per delta T. We're talking about the change in current. Okay? If the current is steady state, if it's not changing, the inductance simply doesn't matter. It's zero. Inductance, like capacitance, these are both reactances. The word react tells you that if the current's not changing, if the voltage is not changing, they go to zero. They simply become irrelevant. Now, we also know that the induced EMF in a coil in a solenoid is equal to minus N times delta phi delta T. Is that right? Yeah. Delta phi, change in flux per unit time. Can you see this well, Cash? Okay. Well, we know phi, the flux produced, the magnetic flux produced inside a solenoid, or around a solenoid, by a solenoid, is equal to mu sub naught, the permeability of free space, times the number of turns, times the current, times the cross-sectional area, that's the pi r squared diameter, the area of the coil, divided by L, the length of the coil. Now, if that's the flux generated, then what is the change in flux? Well, mu sub naught can't change. The number of turns isn't going to change. Area is not going to change. The length is not going to change. That only leaves the current to change of delta I. So let's look at plug this in here. Now we can talk about the EMF, the induced voltage, or the induced electromotive force is going to be equal to minus N times delta phi, the change in flux. So let's write this out. mu sub naught times N times the area times change in current divided by L divided by T. But right here we've got delta I divided by delta T. And what is delta I divided by delta T? We multiply it times minus L, we get this same thing. What, are they going to invert me here? What am I missing here? L delta I for delta T equals N delta phi delta T. Give me a minute here. I don't want to write something up there backwards. Oh, okay. All I got to do is look. EMF, this is equal to the EMF, which is also equal to minus L times delta I divided by delta T. Well, now, if we multiply through by delta T over delta I, we end up with N mu sub naught N squared mu sub naught A over L is equal to L. Right? So change the order. We end up. That is the formula for the inductance of a solenoid, of a straight coil. Everybody getting signed in? All right. All right. Who remembers the units of inductance? Thank you. Henrys. Now, I've already pointed out that inductance, capacitance, they only come into play when the current is changing. What happens when the current is not changing? Yeah, the reactance component, whether you're talking about a capacitor or an inductor, the reactance goes to zero. But what happens to the magnetic field? Remember, it's the magnetic field changing that produces all of these effects. So when you turn on the current and you let it sit at a steady state, as long as that current is flowing, there is a magnetic field produced around that inductor. And that magnetic field has energy stored in it. Okay? That has to be. Think about what that means. As long as there is a magnetic field there around that inductor, that represents stored energy. So what happens to that energy? When the current is turned off, that stored energy of that magnetic field, as it collapses, is going to be converted into additional current to keep the current flowing, at least for a minute or for a moment, until the field is fully collapsed. Now, they just simply give us the stored energy as U is equal to 1/2 the inductance times current squared. How many of you remember any of Physics 1? It does, doesn't it? That looks very suspiciously like kinetic energy. Kinetic energy is 1/2 mv squared. Well, here, the mass, the inertia, and that's all mass is it's the tendency of an object to stay in motion or at rest, whichever. The tendency of an object to resist acceleration, change in velocity. That's inductance. The tendency of a solenoid or a coil or a piece of wire or whatever to resist change in current. So the total magnetic energy stored in that magnetic field is what is analogous to the kinetic energy stored in a mass, a particle of mass m, moving at velocity v. It has kinetic energy, and that kinetic energy can do work as soon as it hits something. You know, as you've all no doubt seen many times over on YouTube videos and late night television. This is magnetic energy stored in that solenoid while current is flowing. Of course, we can rewrite L now in terms of mu sub naught n squared A over L times I squared. Or cleaning it up, okay. They are now going to introduce something called energy density. We've talked about energy density. Have we talked about energy density before? When you store energy in a capacitor, what is it called when you release a lot of energy very abruptly? It's an explosion. That's why lithium-ion batteries, one of the reasons they can be problematic is because because they are so energy dense, they have a lot of energy for a very little mass, and so something happens, they short out, they start dumping a lot of energy very quickly. Well, in this case, the book here, he points out that they can replace I with magnetic field B times L over mu sub naught times N. And so I squared becomes, well, B squared L squared over mu sub naught squared N squared. And if you then multiply this times this I squared, the N squareds cancel, one of the mu sub naughts cancels, one of the L's cancel, and you end up with B squared L over 2 mu sub naught. Did I get that right? Yep. Well, they do away with the L. Yeah, times area. Why did they get rid of the L? Oh, okay, sorry. This is not the energy density yet. This is the total energy stored in the inductor. But the energy density, or the energy stored per unit volume, you divide out the volume, which is simply A times L. And you end up with the energy in an inductor is B squared, the magnetic field, over 2 times mu sub naught. That's the energy density in any inductor of any size. The total energy, of course, would be that times the volume, the length times the area. All right. And that will probably be very interesting to know if it shows up on one of your homework assignments. Not really sure when you're ever going to want to calculate the energy density of an inductor. Now let's talk about an LR circuit. And we're going to get back. This gave some of y'all problems when we were dealing with capacitors. And now it's going to come back to bite you again with inductors. How much current flows through an inductor when you first apply the voltage? I is equal to V over R, right? But when you have when you add an inductor, when you're talking about an inductor, that current doesn't flow immediately. Recognize that? When T, you've got the little lowercase t up top is the time in seconds. This uppercase t at the bottom is a tau, and that's a time constant. So associated with that inductor is some time constant, tau. Now, the current flowing when this becomes I as a function of t. So at t equals 0, when you first close the switch, t equals 0, e to the minus 0 is 1. 1 minus 1 is 0. So in that first instant that you turn on the switch, that you close the switch, the total current flowing is 0. The voltage immediately is whatever voltage is applied. But the current is going to lag behind. Do y'all recognize this from capacitors? Okay. Remember now, we're talking about, like with capacitors, we talked about current, the current immediately started off with maximum current, and then it drained off. It tailed off and dropped down to 0 as the voltage increased according to this same kind of equation. That was the time it took to charge the capacitor. Start draining the current out of the capacitor, the voltage, this equation goes, you stop, you eliminate the 1 minus. And now, the voltage, anyway, keep these straight in your minds, because this is going to be on homework and this is going to be on an exam. You're going to need to think through, is the current building or is the current draining? Which equation do I need to use to describe it? So, who remembers what tau was for a capacitor? Tau was R times C. Well, tau for the inductor is, well, not a lowercase l. Is L divided by R. Right? So this becomes so now when T is equal to R over L, then this becomes e to the minus 1. At t equals 0, this is e to the minus 1. I'm sorry, e to the minus 0 equals 1. At t equals R over L, or 1 over tau, then E becomes e to the minus 1, and that's what, 0.63 or something? 63%? That's one time constant. When tau is 2, t equals 2 R over L, E becomes to the minus 2, which is, somebody else has to do the math. But you see how it increases in time constants. I don't think it's going to be on Monday, but we're going to have one that week. It'll probably be on Wednesday. It'd be kind of mean to give y'all one right out of spring break, wouldn't it? Well, do we have any questions so far? Something pleased you. What happened? What are you finding amusing? Caleb did it. Everybody, let's blame Caleb. All right. Let's do this. I mean, this is an exercise, but I really do want y'all to, somebody break out a calculator and help me with the arithmetic. And yeah, we're going to do 5 time constants again. What's e to the minus 1? 0.63. 1 minus e to the minus 1. 1 minus 0.63. This is 0.367? No, this is, okay. Got it. Point 367, this is 0.63. Okay, what's e to the minus 2? .135, so 1 minus that. .865. E to the minus 3. And 1 minus 0.950. Oh, look at me doing arithmetic in my head. All right, e to the minus 4. 1 minus. Okay, and e to the minus 5. And 1 minus 0.993. All right. These terms are the coefficient that you multiply your base current with. Okay, if you have V sub naught divided by R multiplied by one of these terms, these all represent percentages. Okay, so if it's 1 minus e to the something, you'll notice that the percentages are going higher and higher. That means the current in that inductor is increasing from 0 to 63%, 86.5%, 95% full current after 3 time constants. 4 time constants is up to 98.2. 5 time constants, it's at 99.3%. How many time constants will it take to get to 100%? It'll never get there. As long as you can keep measuring out to more and more and more significant digits, you will never, ever, ever get to full 100%. you will approach it asymptotically. You can get arbitrarily close to it, but this is how the current increases. This is how the voltage increases when you first turn on a circuit with a capacitor. When you first start applying current to a capacitor, it's the opposite of the inductor. With the capacitor, the current starts flowing immediately. The voltage starts to build as it charges. As the voltage charges, the current decreases. The current in a capacitor would be multiplied by this term. In an inductor, this is the term that modifies the current flowing. This would be the voltage drawing, the voltage dropped across it. As the current flows, the voltage across the inductor decreases. Does everyone remember Eli the Iceman? Cash? Okay. Okay, now we're going to introduce reactants. Only they don't actually do it, they just give you an equation for it. Surely they're going to introduce it at some point. Yeah, next page, okay. What is the reactance of an inductor? Anybody know? 2 pi F times the inductance. That is the reactance, the inductive reactance. What's the capacitive reactance? 1 over 2 pi F C. Yeah. When current flows in an LR circuit, I want to follow them along in the book here. Yeah, no, they're also going to point out that V is now you have to talk about VRMS. Everybody remember VRMS? VRMS is V naught over the square root of 2. And of course, IRMS is I naught. Well, I'm going to change that naught to peak. And we did this. Power is... Actually, this did give some of y'all some trouble. Let's look at this again. What is the power? Power is always going to be averaged, because it's always going to involve the square of your peak current, your sine wave. So either I squared R or V squared over R. Okay, but because it always gets squared, power always works out to be an average. So don't write RMS power. Okay, don't write PRMS. It's not right. voltage has a root mean square and the current has a root mean square, because you have to take the average that way, because that's how it works. If you don't, the positive cycle negates the negative cycle and you end up with an average of 0, and that is obviously not the case. Power average is VRMS times IRMS. Okay? Which is peak voltage times peak current divided by the square root of 2 squared. All right. And we talk about Eli the Iceman. In the case of inductors, current lags voltage. Current follows voltage. And it does so by 90 degrees. Now that's true whether you're talking about an inductor or a capacitor. The difference is, for a capacitor, current leads voltage by 90 degrees. So that means or voltage follows current by 90 degrees. So when you start, I don't want to jump the gun. We're going to get to imaginary numbers soon enough, I expect. Yeah, they do actually talk about capacitive reactance here. So, let's talk about a voltage source. There's a resistor, there's an inductor, and there's a capacitor. Right. What does Kirchhoff's voltage rule tell us? We've got this resistance is in ohms, right? But the voltage in this inductor is going to lead the current by 90 degrees. And L is not in henries, is not in ohms. L is in henries. So what we need here is the inductive reactance, which is in ohms. And here we need the capacitive reactance, which is in ohms. Okay? What's the total? And it no longer use the word resistance, because resistance is this part. How many of y'all have done the phasor diagrams and the imaginary numbers? Okay, y'all know where I'm going with this? Okay, good enough. The resistance is the real component of the total impedance. Now we're going to talk about impedance of the circuit, which is resistance. Do y'all use J or I? I or J? I? So in a phasor diagram, R is always along the horizontal line. The reactance will either be inductive up the vertical axis or capacitive down the vertical axis. Okay, so if you have a capacitive component, it becomes minus I x sub c. An inductive component becomes plus I x sub L. Okay, that's plus 90 degrees for the inductance, minus 90 degrees for the capacitance. How many of you remember doing vector conversions? What would be the total impedance? Let's plug in some numbers and do the math. Let's say this is 50 microfarads. This is 200 millihenries. This is 150 ohms. Okay, what's the reactive? What is the inductive reactance? We do need a frequency, don't we? Give me a frequency. 60 hertz. Okay. What's the inductive reactance? 75.4 ohms. What's the capacitive reactance? 52.1 ohms. 53. All right. We've got 150 ohms resistance. So our total impedance is 150 ohms plus I times plus 75.4 minus 53.1. What's that net? $22.3 ohms. That is our net impedance. Before you know anything else about the circuit, what does this tell you? That it is a net inductive circuit. There's more inductance than there is capacitance. How would you write this as a phasor now? As a single vector. What is the magnitude of that impedance? No? Pythagorean theorem. Did you do the math? 23 ohms. That's our net impedance. But 152. 152 is the square root of 23? Ah. Okay. So is this right now? Okay. So it's 152 ohms. But what is the phase shift between the current and the voltage net in this whole circuit? We've got 22.3. This is our net phasor diagram here. We've got 150 ohms and 22.3 vertical, positive. That means our net vector is 152 at theta, where we know the tangent of theta is equal to 22.3 divided by 150. And if we take the inverse tangent of both sides, we get theta equals the inverse tangent of 22.3 over 150, 8.47 degrees. You need to know how to go back and forth between polar and rectangular coordinates. You need to be able to do it intuitively. Because when you start analyzing RLC circuits, and this is where we're going to pick up next time, how do you analyze when all you're doing is resistors, when it's all purely resistive, all real, no imaginary component, no phase shifting involved? How do you find the equivalent resistance of a circuit? You add them together, you divide by you have to do addition, subtraction, you have to do multiplication, you have to do division. You got to do all of it. Put two in parallel, you got to take the reciprocal of the sum of the reciprocals, which means you got to do the division, add them together, and then divide it again. Okay, you multiply, if you're doing two in parallel, what's that? The shortcut, the product over the sum. Okay, you got to multiply, you got to add, and then you got to divide the two. Well, when you're dealing with vectors, to add and subtract, which is just, subtraction is just addition of a negative. You need everything in rectangular coordinates. Okay, then addition and subtraction is easy. Z sub 1 plus Z sub 2 equals z sub 1 real plus I times z sub 1 imaginary plus z sub 2 real plus I times z sub 2 imaginary, z1 real plus z2 real plus I times z1 imaginary plus z2 imaginary. You put them in rectangular coordinates and you just add or subtract it, both parts independently. And you come up with a sum, just like adding vectors. You're adding two vectors together. Multiplication and division, you need them in polar coordinates. Division is simply multiplication by a reciprocal. So whether you're multiplying or dividing, you need them in polar coordinates. Z1 at an angle theta 1 times Z2 at angle theta 2 equals Z1 times Z2 at an angle of have y'all seen this before? Is this new to y'all? No, seriously, is any of this new to y'all?
Is it?
The sum of the angles, theta 1 plus theta 2. If you're dividing, the quotient of the magnitudes at an angle of theta 1 minus theta 2. So, when you start analyzing these AC circuits, these RLC circuits, you start having, okay, this is in parallel with that, and this one is, you do it the same. Put two impedances in parallel, you take the reciprocal of the sum of the reciprocals. But that means first you got to divide one by whatever, and then you have to convert that into rectangular so you can add them all together. And then you take that and you convert it back into polar so you can take the reciprocal again. And then depending on what form you want it in, you either leave it in polar or you put it back in rectangular. Okay, but you need to be able to go back and forth between these. Adding and subtracting. Z plus the two added, you add the real components, you add the imaginary components. And mind the signs. If it's a capacitive circuit, when you add a negative component, you're subtracting it. If you're subtracting Z1 from Z2 and you subtract a negative component, you have to actually add it. But those are simple. That's just the algebra of doing addition and subtraction that you need to be mindful of. Do we have any questions? Anybody got any homework to turn in or any questions about homework or? I will still take late assignments. I will not promise that you'll get credit for them. You'll get credit for them if I have time. I get time to get to them and get them graded. But if I do not, then it becomes a 0, and that's going to kill your grade. Now, this week's homework assignment, week 11's assignment, is due Monday a week from now. It's not due this week. It's due next week, which is spring break. So that one is not due until the Monday we come back. Tuesday when we come back, week 11's assignment will be considered late, which means I will get to it if I get to it. I will be keeping two separate piles. The homework that gets turned in on time gets graded if I have to stay up till midnight Sunday doing it. The work that comes in late gets graded if and only if I can, if I get time. If you have any labs that need to be made up, get them made up. Again, I will still let you make up labs when we get them back, but only if time permits. And I suspect that as we get closer to the end of the semester, I'm going to be getting busier and busier with every passing day.